All right, good morning, everyone. Welcome to my talk on functional thinking. Very often when you start looking at the concepts behind functional programming, you're also looking at a brand new programming language, and it's very hard to divorce the concepts from the syntax. My purpose in this talk is to try to stay very close to languages you know and love, like Java, but focus really more on these functional concepts that you're going to start encountering, even if you're not using a particularly functional programming language, or you don't think you are yet. But I'm going to start with a metaphor, an essay, and a history lesson. So here's the metaphor. Let's say that you're a lumberjack and you're okay. And you're the best lumberjack in the forest at cutting down trees with an axe. It's stunning how fast you can cut down trees with an axe. And then someone comes along and gives you one of these. But they don't show you how to use it, so your first instinct as lumberjack is to swing the uncranked chainsaw against a tree and very quickly reach the conclusion chainsaws are terrible ways to cut down trees. I'm going back to the axe because I've been using that axe for 10 years, feels really good in my hand. Surely there's not a better way to cut down trees than an axe. But then someone shows you how to crank this thing, and you can cut down a lot more trees. The point of this is that learning a new language is easy. We've all done this multiple times in our career because it's really just learning the new syntax around the concepts that you already know. But learning a new paradigm is really hard, and that's really what I'm focusing on this talk. And one of the points I want to make is that functional is really more a way of thinking than a particular framework or language or tool set. It's really a perspective in the way that you attack problems. Here's the essay. Execution in the Kingdom of Nouns by Steve Yagi. This is back from 2006, but it's a terrific essay that's still out there. And in this essay, Steve Yagi posits this imaginary kingdom where nouns are first-class citizens and verbs are subjugated slaves. It's so bad in the Kingdom of Nouns that verbs are not allowed out on the street by themselves late at night without a noun chaperone. And it's gotten so bad that they've invented a special type of noun that has no nounness, that does nothing but chaperone these dangerous verbs around just so they won't get into any trouble. And of course, this kingdom we're talking about is the kingdom of Java, and this insistence that everything be based on a class, which is basically a noun. And for a lot of problems, that makes perfect sense because things in the real world have both attributes and they have behavior. But even in the artificial world of programming, you quickly find that, yeah, you do need to be able to pass behavior around, and then you end up with really ugly things like this. This is a cry for help. What we need here are not more nouns, we need verbs, and not surprisingly, that's primarily what this talk is going to be about. Here's the history lesson. One of the little goodies that you can download from the O'Reilly site is a History of Computer Programming Languages poster. It is nowhere near complete. It only has the top couple of hundred programming languages on it, and there are well more than 1,000 of these things out there. We've been quite busy in the relatively short amount of time we've been inventing programming languages. But I want to zoom back to a particular era for a moment and talk about a particular event back in 1967. And the creation of Simula 67, which is the very first object-oriented programming language. And then in 1971, we got Smalltalk. And then in 1983, we got C++. Now, there's a good, robust argument to be had over drinks as to when did object-oriented programming become mainstream. I don't think it was mainstream before C++ for sure. So that means that there was a long period of time between the discovery of this idea and the mainstream adoption of this idea. You would have thought that back in 1967, when a lot of the programming was doing go-tos and a lot of other really arcane things that we point and laugh at now, you'd have thought that when they saw classes and objects, they would have immediately said, oh yeah, we should be doing that instead of this crazy stuff we're doing now. But that's not what happened. It took 15 years before those obviously very good ideas to penetrate into the way that people use this on a daily basis. And this happens all the time in the computer science world, that you have a kind of a mainstream technology branch, and then you have these offshoots, like academic offshoots, and functional programming started as kind of an academic offshoot. Then you have also practical offshoots. The 4GLs of the late 1990s is a good example of a practical offshoot. But every once in a while, some of these experiments start really bearing fruit, and these branches come back and re-merge with the mainstream. That's exactly what we're seeing with functional programming right now, where the two most interesting languages on the JVM now are Scala and Clojure. F# is now a first-class citizen in the .NET ecosystem. You see a lot of interesting languages like Haskell and Erlang. And in fact, I'm going to suggest that no matter what programming language you're using, you need to start learning how functional programming building blocks work, because it's going to be in your language of choice if it's not already there hiding under something else. So one of the things I wanted to find is a theme for this talk, several themes. And one of the themes that I found on Twitter comes from Michael Feathers, who's most known for writing the book Working with Legacy Code. This comes from Twitter, so it's a little bit tersified by Twitter's requirements. And he makes a very good observation here. He says that object orientation makes code understandable by encapsulating moving parts. Think about the things that you know about object-oriented imperative languages, about how encapsulation works, about how scoping works. There are a lot of mechanisms in those languages to control who can see what and when they can see it, and they can see it, but they can change it. They can see it and change it, and so there are a lot of moving parts around managing state in object-oriented imperative languages. Functional programming makes code understandable by minimizing moving parts. The theory being, if you don't have to interact with that part, there are fewer chances of you interacting with it incorrectly. We see lots and lots of cases. In fact, in lots of the examples I will show you, even in this talk, you'll see this idea exemplified of functional programming removing moving parts because you're operating at a higher level of abstraction and further away from the details that you don't really care much about. So if I want to talk about different coding styles, I need some sort of coding palette to work against. And a little problem that I've used in a variety of situations, and I'll use it here now again, so it works nicely here, is this problem of number classification. And this is actually a very ancient thing. I was just reading Wikipedia around this idea again. Here's the idea of classifying integers. There's a particular thing that you can do with integers. If you take the factors of a number, which are the pairs that when multiplied equal the number, if you add all those factors up and then subtract the number itself and get the number back, that is said to be a perfect number, or it's also known as an ideal number. So it's the sum of the factors of a number minus the number equals the number, or another way of saying that is the sum of the factors of a number equals 2 times the number. So for example, 6 is a perfect number because if you sum its factors, you get twice 6. 28 is also a perfect number. So is 496. If someone wants to start doing long division in the back of the room to verify that, you can trust me, 496 is also a perfect number. And this is the key to this little classification scheme, because if the sum of the factors is twice the number, it's perfect. If the sum of the factors is greater than twice the number, it's abundant. And if the sum of the factors is less than twice the number, it's deficient. So any whole positive integer can go into one of these 3 buckets. I want to write some code to determine this. In the first version I'm going to show you, I won't talk much about the design that went into why it looks the way it does. One of the reasons I chose this example is that this is actually was derived in a chapter of my book, O'Reilly book, as it turns out, The Productive Programmer. This is the free chapter you can download, so if you're curious to see how the imperative version ended up in the shape that it's in, you can download that if you like. But here is the imperative version. This is actually written as an illustration of test-driven development, so it's a very, very well factored and lots of very small methods. And so you see at the very top of the class, we have here a couple of values, a couple of fields that are in there to make testability easier by injecting values. The third one there is I'm going to use it for a lazily initialized sum. I'll show you that code in just a second. My constructor initializes stuff as you would expect it to. The real key of how this thing works is really these three methods. IsFactor really just uses the mod operator to determine if this factor goes into number and has a zero remainder, then it is a factor. And then in calculate factors, I go from 1 up to the square root of the number and look to see if it's a factor, and if it is, I add it. Now, there's a little bit of an optimization going on here because you can make an observation that factors always come in pairs. And so if I'm interested in the number 16, when I grab the factor 2, I can also grab 8, which means I don't have to loop through every number to see if it's a factor or not. All I really have to do is go up to the square root and then harvest them in pairs, which you will notice is exactly what my add factor method does. It takes both of them, deriving the symmetrical factor using the div operator, and harvest all of them in pairs to make this a more efficient algorithm. Now I have some code that sums them up by iterating over that collection of factors that I've created. Now my getSum property here is lazily initializing my sum. So the idea here is, the presupposition is that I may call this once and say, is this given number perfect? And if it's not, then I may call it again and say, okay, well then is it abundant? And so I only want to do the work of summing factors one time, and so now I'm lazily initializing that sum, so the first time through I calculate it, but then I just use that same value for the given number each time through my list. And so there's my little imperative number classifier, and you can make some comments about the shape of this code. It has some internal state for two purposes, one to make it a little easier to test, and one so that I can have my lazy initialization. This code is very cohesive, lots of very small methods that just do one thing each. That comes from being derived from TDD. It's well composed in the Kent-Beck composed method style of code. It's very, very testable. It was actually written as an exemplar of testability, so that's not surprising that it's quite testable. And it is therefore very easy to refactor this code. But let's say that we went into that code with a slightly different perspective. So the perspective that we started with is, I want to make sure this code is nice and testable. But what if we also had the perspective, and I want to minimize shared state as much as possible? So let's see what that version of that code would look like. Still in Java. I haven't moved from Java or done any sort of frameworky stuff. And this is the main difference in that code. I've basically taken three very factored methods before and rolled them into one method so that I can encapsulate the creation of factors entirely within here. That means I no longer have to pass factors around. You'll also notice that number is now a parameter in each one of these methods rather than being an internal field that's set through the constructor. And so I'm passing that as a parameter each time. And in fact, you see this in both of my sum. And mostly you notice it here because notice that this is a lot less efficient now than the previous version. Because now every time I do one of these things, I'm going to have to call factors and sum because I have no intermediate state inside the class to hold on to that and cache it so I don't have to recalculate it every time. We'll see that using some functional programming goodies, we can actually get this cacheability back without introducing shared state. But at least for the moment, it looks like this is not going to be as efficient, particularly if I need to classify the same number for multiple categories. But notice that the class that I have now has no internal state whatsoever, which means there's less need for scoping. The knee-jerk reaction in the Java world is to make everything private because information hiding is a very, very important thing. But here, because all these methods rely only on their parameters, there's no reason to make them private. In fact, I make them static and public because these are potentially useful outside this little class. For example, that factors guy, if I need to go and generate or figure out prime numbers, I need that thing that gets me the factors of a number. And by making this static and public, I can easily reuse this. In fact, this is a muscle that is really, really atrophied in many, many Java developers. You never think of reuse at the method level. You only think of it at the granularity of classes because you're so accustomed to classes as a reuse mechanism, but you can actually, in many cases, get a much more granular level of reuse by having pure functions like this. This code is still very testable, and it was written TDD, just like the other code was. Still quite refactorable, although it is a little less cohesive than the previous version. I have lost my lazy initialization from now. I'll actually get that back in just a bit, but for now, it looks like this is slightly less efficient. But I think this illustrates the point that I was making earlier, that functional is more a way of thinking than a particular tool set. It's a perspective on how you attack problems. Now, when you start looking into functional programming, you'll see that it's a pretty deep and wide ocean, and there are all sorts of fascinating little places that you can bump around in the functional programming world. I don't have a lot of time in this talk, so what I'm going to do is take a few subjects from the functional programming canon and talk about how they are kind of applying to us in our current world. The first of these I'll talk about are higher order functions or first class functions or lambdas or whatever you want to call them. This is typically the mathematics definition of this term. Computer science typically calls these first class functions, but in any case, these are functions that can either take functions as arguments or return them as results. This actually solves a big deficiency that has been band-aided over in a whole bunch of different programming languages. And let me show you how that Band-Aid works by presenting you a really common scenario. This is an example from one of my other talks. It is the target of a refactoring exercise. And you refactor this big, ugly blob of code down to here, and you realize that, well, you know the two lines that start with add there, if I replace those, what I have is a pretty good generic template for doing transactional data access. This is part of this exercise of refactoring to find design elements that you can suck out of code. And so how would I achieve that result in the Java world? Well, the way that you do this in the Java world is use the command design pattern from the Gang of Four. So you build a little wrap-in transaction method that takes in a command. The command has an execute method, and then now your add order from method becomes this wrap-in transaction, create a new command, create a new method, and put your two little add pieces in there. This is really just a cry for help. Please give me higher order functions, because all this is just kind of a train wreck of accidental complexity around the deficiency that we don't have a really useful way to pass around behavior. So if you look at this exact same code in a language that does have higher order functions, it gets way simpler. Not only can you drop some of the parens and other things, but in the Groovy world, everything in curly braces like that is a code block and is automatically a closure. And so you don't need the command design pattern in this world anymore. In fact, once you have lambdas, it deprecates the command design pattern forever. There's never a need to use that thing again, because that is two names when you need no names. You just need to pass functionality. But the other interesting thing about this code block that you end up creating in Groovy, it is not just a code block, it is also a closure. And that's one of the other features that you see very commonly in these languages that are supported by lambdas and higher order functions. But I want to talk for a second about what's so special and magical about closures. And I wanted to put together the smallest example I could that illustrates what sets closures apart from different kinds of method and function constructs. And so I did so in Groovy. So here's my example. So I have a little function here called makeCounter. And what it does is define a very local variable and set it equal to 0, and then it returns a code block. Now, I don't even care what the code block does for the moment. Just observe that it returns a code block. So in the subsequent code, when I say C1 is equal to makeCounter, C1 is now pointing to an instance of that code block. When I say C1 open and close parens, it will execute that code block. And so what happens when you execute that code block? I say very local variable is equal to very local variable plus 1, and Groovy, like many expression-based languages, the last line of the code block is the return value for the code block. So if I evaluated that first call to C1, I would get a 1 back. And then I would get a 2, and I would get a 3. But then I come along and say C2 is equal to make counter. Underneath, we know what's going on here. Both of these guys are firing a constructor and instantiating a new instance of this code block guy. But now when I come down here and execute this last line of code and print out my C1, I'm up to 4, but C2 now equals 1. And this is the thing that's unique about closures, because it turns out that both C1 and C2 have their own unique instance of a very local variable. In most languages, very local variable would be out of scope by the time make counter exits. But this is the unique thing about a closure, because when you instantiate that closure block, it encloses the environment that is currently in scope and keeps it alive. That's why it's called a closure, and it creates this enclosed environment around all the things that it can see are in scope and creates a unique instance of that and keeps it alive for the life of the closure block. And when that closure block finally goes away and gets garbage collected, then all the references it's additionally hanging on to get collected as well. This is a great example of what I was talking about before, a great example of hiding moving parts. The language is now managing that state for you for this local variable. You don't have to write a getter and a setter for it and maintain that thing, because it's being maintained entirely for you. And so this is really nice because we can let the language manage that state for us rather than be forced to manage it ourselves. And this is a really important idea, because over time, we cede more and more busy work to our languages and runtime. Now, back when I was in university, back in the early 80s, we were using this thing called Pecan Pascal. And it was really cool because you could write Pascal programs that would run on both the Apple II and on the IBM PC. And the way that worked was when you compiled a Pascal program, you didn't compile it down to machine code. You compiled it down to this stuff they called bytecode. And they had written this thing called a virtual machine that ran on each of those two pieces of hardware, and it was slower than Christmas. It was crazy how non-performant it was, even for college projects, because we just didn't have enough horsepower in our computers at the time to support that model. But then you fast forward 10 years later, and Java now is doing the exact same thing, and we have just enough overhead to handle that. Over time, we cede more and more busy work and plumbing to our languages and runtime. I've worked in a lot of languages that didn't have garbage collection, been there, done that, got the t-shirt, don't want to go back. Life is too short for malloc. There's a better way to spend your time than chasing down memory problems on a computer somewhere. We have mechanized ways of handling that. And that's exactly what's happening in all your languages. We now have enough overhead so that you can really start adding these much higher abstraction functional programming constructs to languages like Ruby and Python and Java and Groovy. All these languages have the facilities to take advantage of this now because they have enough overhead to handle this. Even some radical things like Clojure. I did a workshop yesterday. One of the things that's really cool about Clojure is that it does for concurrency what Java did for garbage collection. You can write really high-performance, multi-threaded applications in Clojure and never once think about synchronized blocks or concurrency or threads or any of that stuff. There's a really fascinating thing that just came out recently. Rich Tiki is talking about reducers. And basically what he did was figure out a way that there's a drop-in replacement now in Clojure so that every time you do a map operation, it automatically parallelizes across all the processes on your machine. You don't have to worry anything about that. It's completely handled for you and guaranteed to be safe. So over time, we cede more and more to our language's runtime, and you should encourage that and embrace that idea. Even things like tests, there's some really fascinating stuff going on, things like specification-based testing frameworks. And that actually gets us to another interesting dichotomy between the functional programming world and the object-oriented imperative world. Because in the object-oriented imperative world, the way to achieve code reuse is to build classes with messages between them. So it's not surprising in the seminal work in the field, design patterns, elements of reusable object-oriented software, every single one of those comes with a class diagram. Because that's how you solve problems in that world, are networks of classes that message one another. This is typically not how they're trying to achieve code reuse in the functional programming world. Instead, what they're trying to do is encourage using just a few core data abstractions, rather than build a unique data abstraction for every problem. How many XML frameworks are there for Java now? Has it reached triple digits yet? It's got to be getting close at some point. And every time you build one of those, you're building unique data structures instead. Instead, for example, what Clojure does is as soon as it encounters XML, it mashes it down to a data structure, a map data structure that it already knows about and has built machinery for. So functional programming languages tend to build hyper-optimized machinery around just a few key data structures, like lists and maps and sets. And what you're expected to do is take data in some sort of data structure and augment that with a higher order function that customizes the machinery. This plugs into the gears of the machinery and customizes what it does to your data so that when you pass it in the machinery, it undergoes some sort of interesting transformation out the other side. So let me show you what I mean by that. Let's take my number classifier problem and solve it using functional Java. Now, this is a framework in the Java world that tries to add as many functional concepts to Java as it can without changing the syntax. So we don't really have higher order functions, but we cheat with anonymous inner classes and generics. One of the nice things about functional Java is that it's very svelte. It doesn't download an entire Maven's worth of jar files to make it work on your machine. It's just a single jar file, and it works with any Java 1.5 or greater. So let's see what my number classification problem in functional Java looks like. And here it is. And let's look at a few of the really changed methods like this one. So my sum has now become return factors.foldLeft add comma 0. How is that summing something? Well, first of all, notice that's not a native Java list. That's a functional Java list because native Java doesn't have a fold left method. The other thing that's kind of mysterious is that add guy. That's being sucked in by a static import. So that's actually its fully qualified name. That is basically a function that takes in two values and returns the sum of them, as you would probably guess by its name. What's happening here is that fold left is a list transformation. So my goal here is I have a list, and I need to convert it down to a single value. And the single value I want in this case happens to be the sum. So the way that I'm going to do that is take the second element of the list and fold it in on the first element of the list. And what I'm going to use to fold it, well, it looks like I'm going to use add to fold it. So I fold the second element in on the first one, and then I do that again with the new second element, fold it in on the first one. And by the time I'm finished, what's left is a single value that represents the sum of all those things. That's how I'm doing the sum, is doing this fold operation. Now you notice I did a fold left here, and obviously with addition it doesn't matter. But there's also a fold right if you have an operator that where order matters, you need to go the other direction. And this is called different things in different languages. And in fact, for example, if you look at Clojure, where this is built in, well actually I wanted to show you, there are actually a bunch of these little guys pre-built for you, and I'll show you how you can build your own in a second. If you look at a language where this concept is already built in natively, here's the exact same code in the Clojure world. Clojure is a list, so you sort of read inside out. I'm defining a function called SumFactors that takes number as a parameter. Factors of number returns the list of all those factors. And then reduce says take some function, plus in this case, that takes in two parameters and returns a single result. Any function that takes two parameters and returns a single result can go there and then apply it across that list. So that's how I'm doing my sum. And notice I'm not thinking about iteration here. I'm thinking about list transformation. I have a list. I need to transform it and generate the sum. So I'm thinking about the results and not about the steps required to achieve those results. So the astute of you will have noticed that there were actually 2 instances of iteration in my slightly more functional version. So let's go attack the other one. The other one was determining the factors of a number. So let's say that my target number is 12. How can I determine the numbers of 12 without iterating over and touching each one of them? Well, I can make an observation that it's going to be some, but probably not all of these numbers. These are all the numbers that it could possibly be, and that suggests a filtering operation, which is exactly what I'm going to do. Factors of now returns range of 1 to number plus 1, because ranges are non-inclusive in functional Java, dot filter. What filter wants is a higher order function that describes something I can execute against each thing to decide should you be in this list or not. So it's going to return a Boolean. So this is the conceit in functional Java, where I use this helper class to create a new class that accepts an integer parameter and a Boolean return, and then the f function actually takes in my integer and calls my is factor. That'll return true or false. And when this is done, I'll have a filtered list. Now, here's an interesting observation, though. Is this more or less performant than the original imperative version of this code that I showed you? It's actually, for right now, quite a bit less performant, because this one is visiting every single number. It doesn't have my slick little square root optimization lurking in it right now. I'll fix that in just a bit in a functional way, but notice that in the naive case, this one's going to be a lot less efficient because it's going to do a lot more work. But you'll also notice I'm not doing any iteration here. All I'm doing is transformations on these 2 data structures. And a good example of this idea of think about the results you want to achieve, not the steps required to achieve it. Now, I do not for one moment suggest that SQL is a functional programming language. It is actually an interesting amalgam of a bunch of different paradigms, but it does have one important analog here, in that when you issue a SQL query against your database, you don't tell it how to allocate memory and where on the file system go get that stuff. In fact, you can't even see its file system. You just tell it what you want, and it comes back with the values. And that's what functional programming is trying to do all the way down at your language level, so that you can think about results and not about the steps required to achieve those results. But just like in a database, most of the time that's cool. But what about the times when you really want to think about the steps? You could do the same thing here. It just requires thinking about the problems in a slightly different way. So, for example, in my imperative number classifier, one of the slick things about it was I had this square root optimization in it. So how can I get that back in my functional Java version? I can, like this. So what I'm doing here is saying the first part, I generate a intermediate value factors, which is range up to the square root of the number using my is factor. What this is going to do is generate me all the factors up to the square root of my number. Then I'm going to factors.append onto that list factors.map. This is yet another transformation we haven't seen before. What map does is say, take this higher order function and execute it against each element in this collection and return me a transform collection. And the thing that I'm executing on each element is saying, generate the symmetrical value for me. And what that's going to do is generate the values above the square root. And you'll notice this last little line down here, nub. This is because functional Java, while it should have the same set of methods on sets and lists, is missing some of them on lists. But you can convert this back to a set using nub. And this was discovered by a unit test. So functional programming does not absolve you the responsibility of writing unit tests. But this does make it easy to convert back and forth between a set and list. So a good example of thinking about results, not about steps. In fact, this is a good example of what I was talking about before, the way we try to achieve reuse in the functional programming world. It's really more about transformations than it is building unique data structures. So we saw this fold or reduce Catamorphism or transformation on lists. That's one way to take a list and convert it down to a smaller list, usually a single value. You can also do filter, which is usually a subset of the bigger list. And we also saw this mapping operation, mapping things on top of one another. This is really a fundamental change in the way you think about problems, because you have these fundamental transformations. Now you start thinking about, how can I get my problems into these shapes that I already understand? So what if you wrote this classifier guy in a language that already supported all this cool stuff? Like Groovy. So there's my is factor. That hasn't changed. My factors of now does one ... number. That's a range in Groovy. Find all. This is Groovy's version of filter. And the code block I'm passing says is factor and number, comma, it. Now, I have to explain a little bit about what's going on in this little snippet of code. That, obviously, is the range of numbers. There's my find all method. You'll notice this is a code block, and this is factors it thing. This is a really common syntactic sugar in Groovy that a lot of languages have. It could be written like the version I have below, but anytime you have a single parameter to a code block like that, rather than specifying the parameter and just repeating it in the code block, you can just use the word it. That's a reserved word in Groovy, so that makes that a lot cleaner and prettier by doing that. There is my reduce in the Groovy world, which calls it inject for whatever reason. Factors of number dot inject. 0 is the seed value, and you'll notice that's a code block that takes in two values and returns their sum, which is exactly my goal for my sum. And then finally, my is perfect, is abundant, and is deficient. Now, one of the cool things about that is that those are pure functions. And you can do some really interesting things with pure functions. Now, most of the time in the past, you only cared about pure functions because of things your runtime could do. And in fact, your runtime can do some really nifty things with pure functions. Like if the result isn't used, it can strip it out, or you can do parallel execution, or you can change the execution order if you only rely on your parameters. But now we have some opportunities to take advantage here, because you can make an observation about a pure function. A pure function is one that relies only on its parameters. So for example, the math.tangent function in Java is a pure function. When I call math.tangent of 19 this week and math.tangent of 19 next week, it had better give me the same value. The observation here is that a pure function with a given set of parameters always yields a constant value. And that enables this cool feature called memoization. So let's say that one of the requirements came about for my classifier guy that I need to cache the sum, so I don't have to recalculate it over and over again. So that's easy enough. I go into Groovy and I say, okay, well, I'll create a map. That's a member of the class. I'll initialize it in the constructor. And now in my sum of factors, I look in the cache and see if it's there and return it. Otherwise, I calculate it, put it in the cache, and return it. I'm sure most of you have written some handwritten caching code like that at some point in your career. But never again should you have to do that, because as long as that thing is a pure function, and my sum factors here is a pure function, in the Groovy world, you can say sum of factors is equal to sum factors.memoize, and shazam, you are all done. The runtime will now cache these values for you. I wrote up an article series about this, and I talked about memoizations, automatic caching, and you can memoize at most this many elements and memoize at least this many elements. And I tried as hard as I could to write a handcrafted cache in Groovy that would outperform theirs, and I got nowhere close, because you know why? They cheat. They have access to things that I don't have access to, internal data structures and other things. They are always going to be able to write a better cache than I can, so why not let them? Stop handwriting little fiddly bits like this and let languages and runtimes do those things for you. Remember back in my Java example before, I was lamenting the fact that I had lost this my lazy initialization. Well, that guy is a pure function, so if I did this code in Java 8, I could get it back, because Java 8 supports memoization because it supports lambda blocks. A great example of eliminating moving parts. If you don't have to handwrite a cache, you can't mess it up in some way when you've written it, and that frees your head up to think about the problem you're trying to solve, not the plumbing required to solve the problem you're trying to solve. So to summarize, in many ways, the functional programming concepts are new ways of thinking about old problems. Stop thinking about everything structurally and start thinking about smaller elements of reuse, and start thinking at a higher level of abstraction. That's the real win here. Cede control to languages and runtimes as quickly as you can. Let them do heavy lifting, and only step in when you absolutely have to get down to nitty-gritty details about things, because you really want to start thinking at a higher level of abstraction. If you start looking at languages like Scala or Clojure that really encourage this style of development, it's really remarkable how much the amount of code you have collapses because you're working, each line of code that you write is doing the work of 10 or 15 lines of code in an imperative world. Learning all these concepts now are heavily aligned with language trends. All the major languages are adding these functional concepts because now we have enough overhead to make them feasible to do that. In fact, there was just a book that came out about functional JavaScript from Michael Fogus, so even the JavaScript world is on this bandwagon. And this gives you new ways of thinking about problems and gives you solutions to problems that you may never have come up with before. I think the Clojure community in particular is doing a lot of really remarkable outside-the-box kind of thinking about problems. So for more information about this, I've got an article series on IBM Developer Works right there. I'm also writing a book for O'Reilly, and also have a video called Functional Thinking, which is this talk in about 4+ hours worth of stuff. I've exactly reached the amount of time that I have allotted, and I realize that we're immediately prior to lunch. So I'm going to set you free. Thank you very much for coming, and I hope you enjoyed it.